Hello all. Welcome to the class Math 110, and I will wait for a second. Hello all. Welcome to the class Math 110 from Advanced College. I am your teacher, Professor Moody, and I will be hopefully showing you the ways that we are going to be computing basic mathematics and also understanding mathematics a little bit clearer. Okay? Ah, yay, cool. So, first things first. One thing that I want to stress in this class is that mathematics builds. Okay? So what I'm trying to do, what I will do my best in order for you to understand, is to start at a base, a strong base, and build something that might seem a little bit unnecessary, but believe me, it's for a purpose so that way we can build on top. Okay? Now, when I say the bottom, I mean the very bottom. Hence why I wanted to ask how long it's been since you have taken a math class, which some of you stated that it's been up to 10 years, some people 12 years, Whereas also some people have just taken a year off and they took a mathematics class last year or 2017, so like about half a decade, that kind of thing. So that being said, I am here to hopefully facilitate and to help you understand more about mathematics and the basic uses of it. So the first thing that I'm going to start out with is a question for you. Okay? When we were in grade school, there was one thing that we had to distinguish first. Okay? We had to distinguish numbers being different. All right? Now you might look at me and say, that doesn't make any sense. But if you think about it, right? When we were in grade school, we said this is 1 and this is 2, right? 1, 2. Okay? 1 is less than 2. That's the relationship between those two numbers. Okay? So, how do we write that in mathematical language? Okay? First of all, we put our symbol. So, of course, everybody knows what a 1 looks like. And then 1 is less than 2. Okay? That is a relationship between two whole numbers. Okay? Now, when we start getting into negative numbers, we get into what are called integers. And the integers is a set of numbers where you have 0 included, as well as negative numbers. Okay? So now, for integers, we have -1, 0, 1, 2, and going over here, and so on and so forth. Okay? So, whole numbers, right here, integers. Integers is what we will be using more of. And let me go ahead and spell that word out for you so that way you can put it down on your notes. These are integers. Okay? And integers is nice because in integer land, everything is full. Okay? If we're wanting to think about it in dollars and cents, everything is in dollars. Okay? There's no need for any of the decimal points or anything. Okay? In integer land, everything is exactly. Okay? So you can't have 1.5 books. It's 1 person, 2 people, 2 books, so on and so forth. Okay? That is the set that we are going to be developing first. Okay? And to kind of give you an overview, we will be going into rational numbers later, or rational expressions. So let me go ahead and write that down. Just so that way you can put it in your notebook. And this, I'm going to star too, to say that we will talk about this a little bit later. Okay? So, integers is what I want to focus on. All right? Now, let's go back to our original question, okay? Or not really a question, but the first expression that I made. Or equality, inequality. This is an example. I guess I should probably start with that. So, when something is not equal it is unequal. Therefore, this is an inequality because it's not equal, not the same, right? And we have to distinguish whether things are the same or they're not the same. And that is why we use this symbol right here. Now, there's 3 of those relation symbols that are known as parts of the inequality. Okay? So, the inequalities are as follows. They are that direction, the one that's listed right here, okay? And the other one that we will use for inequalities is when we don't know if they are equal, is that equal sign. Okay? These are the 3 ways that we are going to be relating the set of numbers that are called integers. All right, so follow me so far? Okay, good. Another thing I want to express is when we were probably learning integers back in grade school, I'm sure that they talked to you about a number line. Okay, so this is the idea of a number line. Right? It's a line with numbers. Wow, we mathematicians are just so creative, right? Not really, but that's beside the point. Okay, so to the right of 0 is going to be 1, 2, 3, blah, 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 right? Because we're in integer land, to the left of 0 is going to be -1, -2, -3, -4, blah, 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 blah. Okay? Now, let me ask you this question. This number right here, this 3, is that 3 bigger than that 0? Well, obviously, yes. You can have nothing, and you can have 3 of something. You'd probably rather have the 3 of something, right? I mean, unless the 3 of something is something that brings about a negative response, but don't worry about that. So, 3 is bigger than 0. And 3, or the number that is bigger than 0, is on the right side. Okay? So, the number on the right of the number line is a bigger number. Now, why do I say that? Well, positives, everybody's fine. I know that that number is bigger than that number. Duh. I've been there, done that. Let's look at the negatives. When we look at the negatives, which number is bigger? The -1 or the -3? Now, if our rule follows the same premise, then let's look here. The number that is further right is the -1. So therefore, -1 is bigger than -3. Or in other words, using our inequalities, we would write this. That, and I'll write it in orange because that's the color that I used there. -1 is greater than -3. Okay. Now I want you to examine this relationship between these 2 inequalities right here. Okay. And let us say, instead of using -3, let's use the same numbers of 1 and 2. Okay? All right. And if that's okay, I'm going to erase our number line. So, 1 and 2. Now, let's say they're both negative. Okay? So, -1 versus -2. Which number is bigger? All right. Well, using the argument that we just posed, the -1 is bigger. Look what happened here. You see it? The sign of the inequality flipped. So whenever we negate an inequality, it changes the sign. All right. Let me further try to explain this, okay? Let us then, instead of changing the sign of both of them, let's look at it if it were one of them were changed. Okay, let's still use 1 and 2 because, might as well use nice and easy numbers. And this is the nice thing about mathematics, and I'm hoping that I express this to you and you understand this. In mathematics, if it works for one case, it should work for all cases. Mathematics is universal in that aspect. Okay? If you find that it only works for a couple cases, it's not true. Okay? That's the one thing that we have to make sure to watch out in mathematics, is that every possible case is covered. Okay? All right. Awesome. Sorry to be a little bit strict there, but remember, we are building a foundation, and the foundation must be built on fact. All right? Okay. So, 1 and 2. Let's negate one of them. Let's negate the 1. Okay? If I negate the 1 right here, right, then obviously the 2 is going to be bigger than -1. Right? Okay. Now, let's do... Here, hold on. You can't see that. There we go. Now you can see it a little better. Okay. Now, let's negate the expression. Okay? So, -1 and a -2. Now, according to our rule, whenever we multiplied it by a negative, or whenever we changed the sign, the inequality flipped, right? So, my question to you is, how do you think that's going to be possible? How is it where we have a negative is bigger than one negative? Okay? So I want you to think about that for just a little bit. Okay? And I do apologize, but outside they are cleaning my windows, so that's the strange sound that you probably hear right now. Okay. All right. Well, the reason why this still works, or the only reason it would work, is let's think about this. When is 2 less than 1? When can the number 1 be bigger than 2? The only way possible is that the sign is different. Let me say that again. The only way that 1 can be bigger than 2 is if the 2 is negative. That is the only way. Okay? Therefore, the only way that 1 is bigger than -2 is this. 1 must be positive. That's the only way. Otherwise, we start getting into this way of having triple negatives, quadruple negatives. We don't want that. This then creates another theory, or another theorem. Okay? -1 times a -1. And by the way, that's the operation that we're going to be... Oh, can't see that. Okay. -1 times -1 equals to a positive 1. Okay? And that is going to help us out. Now, once again, this dot right here that I wrote, that is what we will be using in this class, is the operation of multiplication. Okay? Okay. So then, technically, if I write a number on the board, the implication is that it is positive. Until I write a negative in front of it. Okay, do you follow me? So, whenever we write numbers, they are always positive. It is only until we attach a specific sign to them do they become negative. Okay? The other thing that I want to show you, or that I showed you just now, is that a negative times a negative equals to a positive. Okay? Negative times negative equals positive. All right. Now, the reason I show you that is because in order to have this negative here, to negate this thing, what we are doing is we are multiplying. We are multiplying the expression by a -1. That is how you change the sign of a number. You multiply it by a -1. Okay? Okay. So that is a overall, at least, talking about, and this will be the answer to some of your discussion questions that I'm hoping you will answer, involving inequalities and integers. Okay? So, now that we have spoken about integers and inequalities, let's go into second grade. Okay? Because right now, all of this stuff right here, of course, the inequality stuff is a little bit different, but that's just because it was taught to you a little differently. Okay? In second grade, we talked about the first operation, besides the relationship between two numbers. And that operation is addition. Which you can all roll your eyes at me right now and say, well, Mr. Moody, addition is super easy. And I get that. That is okay. Like I said, I am building, and I know I keep stressing this, and I do apologize about that, but I am building a strong foundation. So that way we can build on top of it. All right? Okay. Now, that's all right. I'm going to go ahead and erase the board. So, I just told you about a other word besides the inequality, right? And that is a operation. Okay? Now, operators or operations are processes you do with two or more numbers. Okay? And these processes include addition, subtraction, multiplication, and then division. Okay? These are the operations on numbers and values that we use to compute different scenarios. Okay? So, the first one, of course, is addition. So let's talk about addition. Okay? Let's go ahead and erase these other operations for now, and let's keep addition up here. Okay. Now, of course, this is going to be the easy part of the presentation. But that is okay, because once again, and I know that I've just stressed this, but I cannot stress this enough, mathematics builds. Okay? So let's see here. Let's just pick really small numbers for now, just to look at them. Okay? How about 2 and 3? 2 is different than 3, right? So let's look at that case first, that both numbers are different. Okay? So we've got 2 and 3 and our operation between them. Okay? When we're adding 2 and 3, what we are doing, right, is we're taking 2 and then we're adding 3 on top of it. 1, 2, 3, right? And that number of fingers is going to be the answer to that solution. Now, my question to you is 5 bigger than 2? Well, obviously it is, Mr. Moody. I mean, you had 5 fingers versus the 2 fingers. these have more fingers than these do, right? And once again, you can roll your eyes at me if you would like to. I do not take any offense. 2 plus 3 equals to 5, or 5 is bigger than 2 and 3. Therefore, addition increases. Okay? Addition increases the value of the number. You follow me? Okay? So, when everything is positive, it increases the value. Okay? Now, remember, we're dealing with integers, right? So let's start putting some integers. Let's make both of them negative for now. Okay? Negative 2 plus negative 3 equals to what? Now, I know some of you are thinking, well, don't you just subtract them? Yes and no. Okay. You're not really subtracting. It's still addition, right? Okay. But let me write it another way. This is the exact same expression. As you can see, these expressions, the negative 3 looks very different, right? This looks like negative 2 minus 3, or negative 2 take away 3, versus negative 2 plus negative 3, right? But they are still the same expression. Okay? All right. So, let's look here. The 2 and the 3 are obviously positive, right? They have what we call the same sign, right? The same sign, we add the two numbers, and what's the sign in front of the 5? It's a positive. Let me pose it to you a different way. Whenever I'm dealing with negative numbers, I like to think of it in terms of money, and I'm hoping that it will help you students out when you think about it this way. Okay, so let's say that the negative is something that you owe the bank. Because you notice that they always have that little negative and parentheses and things like that. That's what you owe, right? The positives, or the thing that doesn't have a sign attached to it, is the positive. That's what you have, right? Or that's what you've gained, okay? So now, let's look at it this way. I went to the store and I bought, I don't know, for $2, you could probably get, let's say, candy bar. King size candy bar. So it's like $175 plus tax, more or less, right? So it costs $2, right? Okay. And then let's say that you got something else, like I don't know, let's say you got a thing of say like aluminum foil, something like that, right? Like a smaller roll of aluminum foil. It's more or less about $3, right? Well, how much money are you going to lose out of your pocket? Because it costs 2 and it costs 3, right? So 2 and 3 gives you how much money did you have to spend? You had to spend $5, right? And notice this. The negative, negative, negative. The sign was the same. Therefore, I added the two numbers and just attached the sign. Okay? Let me say that one more time. These signs are the same. Okay? Therefore, I added them, the two numbers, and just attached the sign. Okay? So, similarly, if we look back at the first thing that we looked at, right, with the inequality, when I negated the entirety of the expression, or the inequality, it flipped the sign, right? It was positive, now it becomes negative, because I multiplied all these things by a negative. Okay? That is what I want you to be thinking of. That is how addition works with integers. Now, let's look at another case, because right now we have the case where the signs are the same, right? What if they're different? Let's go ahead and flip the order if that's okay. It might make it look a little nicer. Okay, and then I'll also do this one. All right. Well, remember, the 3 plus negative 2 is the same thing as saying 3 minus 2. Okay? And what is 3 minus 2? Well, it's 1, right? But how do you know that? I had 3, take away 2, 1, 2. I'm left with just 1, right? Therefore, the 1. But why is it not a negative 1? Why is it a positive 1? Well, let's look at it this way. Both these signs are the same, so the sign is going to be the same here, right? Both these signs are the same, so the sign is going to be the same here. These signs are different, but look at the numbers themselves without the sign, okay? Which number is bigger, the 2 or the 3? The 3 is bigger. The 3 is bigger, so the sign that's in front of the 3 is attached to the answer. It's a positive 1. Okay? All right. Now, let's take a look at this one using that same logic. Okay? The signs are different, so I subtract. So, the signs are different, so I subtract those two numbers. Okay? Well, we just found that by subtracting them, we get 1, right? However, what number is bigger, the 3 or the 2, without looking at the sign? The 3 is bigger, right? And what's the sign attached to it? A negative. Therefore, we have a negative 1. Okay? This right here is how we add integers. Okay? Now notice, I've done nothing about subtraction. Okay? And that is true, because I'm hoping I can teach you that subtraction doesn't technically exist. Subtraction is the addition of the opposite signed number. Now, what do I mean in English? Subtraction is the operation of addition with a negative. Okay? So, here, right? 3 plus negative 2. Whereas we could write it as 3 subtracting 2, right? But once again, this is a manipulation of this. Now, why do I say that? Let's go back to our multiplication principle that we thought of, right? So, our multiplication principle is that when I take negative 1 times a negative 1, I get positive 1, right? Well, what if I just take 1 negative 1? 1 negative 1 would be negative 1. Why is that the case? Let's go back once again to our inequality. When we multiplied everything by a negative 1, the sign changed. When we multiply negative 1 by a positive number, the sign changes. The implication is that there is a 1 in front of the parenthesis right here. That is the implication. Okay? And 1 times a negative number equals to 3 minus 2. Okay. And don't worry, if you don't really understand about the multiplication, we will go through that a little bit more in detail. It is called distribution. Okay? All right. So now that we have discussed the addition of integers, okay, let's now go into the multiplication of integers. But before we go into the multiplication of integers, we need to address some specific type of numbers. Just like we've talked about with integers, that there's positives and negatives. There are also what we call primes and composites. Okay? All right. So let's see here. How do we multiply integers? And what does Professor Moody mean by prime and composite? Well, let me go ahead and also get rid of our operation for now. And let me ask you a question. Have you ever used, or have you ever heard of, a thing called a factor tree? If you haven't, this is the idea behind a factor tree. 2 multiplied by 3 equals to 6, right? But instead of putting 6 here, I'm going to put it on top of these. Okay? Hence why you get what's like a tree. For those of you that are a little bit more learned in mathematics, this is known as prime factorization. Okay? All right. So 2 times 3 equals to 6, which is the same thing as saying 6 is on top of these guys. Okay? Okay. Now, let me talk about these 2 types of numbers, because there are 2 types of numbers that are listed right here. Okay? There are, like I mentioned before, prime, okay, and then there are what we call composite. Okay, so prime, composite. All right. I will go ahead and highlight the numbers or square the numbers that are prime. Okay. Now, I'm going to circle the number that's composite. Okay. So now, looking at this number, do you see what is prime and what is composite? I'll give you a couple minutes to think about that for a second as I take a drink. Okay. So, composite is a number that can be broken apart into primes. Primes build composites. Okay? That is the idea with a factor tree and primes versus composites. Okay? Now, let's see if we can find some more primes to understand it a little bit further. Okay? Let's see here. Well, actually, let me ask you this question. And let's see if you can answer this. Okay. Well, I mean, of course, you're watching the video, so answer it on your paper. My question is it prime or is it not prime? And we haven't really discussed about the primes, really, right? But remember, a composite is a number that can be broken down, okay? 6 equals to 2 times 3, right? Okay. So, 17. Let's think about this carefully. if a composite is a number that's broken up, did I put any fractions up there? No, I didn't. A composite is built of integers, of prime integers. So let's look at 17, okay? And let's ask ourselves, does 2 times something equal 17? Unfortunately, no. Let's look at 3. Does 3 times something equal 17? Well, we have 3 times 5, which equals 15. And then 3 times 6 equals 18. So 17 is not a multiple of 3. Okay? How about 4? 4 goes into 17. Well, 4 goes into 16, right? But does not go into 17. Okay? And you could keep going on to see if it's a prime or if it's not a prime. Okay? But what I'm going to tell you is kind of a shortcut. Okay? With establishing whether it's a prime is when you have the number squared is going to be a little bit less than that number or a little bit more than that number. What do I mean by that? Well, two times 2 equals 4, right? 4 is a lot smaller than 17, right? Therefore, we have to keep looking for primes. 3 times 3 equals to 9. Okay. All right, we are getting closer to 17, but we're not there yet. 4 times 4 equals to 16. Right? And because we're talking about factor trees, let's make these into looking like factor trees instead. Now notice, 4 was already broken apart, so 4 is not a prime, right? It's a composite. Therefore, I can break those into more 2s. Okay. All right. But now look, 4 times 4 equals 16, right? 16 is just shy of 17. If we were to go 5 times 5, we'd be above that number, right? Which means cannot be a possibility that 5 and another number can break apart 17. Okay? So what I'm getting at, this is a little bit more of an advanced concept, but I'm just trying to help you with this whole factor tree business. Okay? The idea is that we only stop at 4. We don't have to keep looking for primes. We can now say that 17 is, in fact, prime. Okay? Now, you may start to notice a lot of the odds are prime, and that is true. But let's look at some other ones. And I'm going to go ahead and erase these guys too. And from now on, whenever I'm using multiplication, I'm going to do it in a factor tree type, okay? Type format. How about 21? Okay. Well, first, let's see how far we need to go, right? So, once again, we have 4 is 2 times 2, right? Still too small. Gotta go more. 3, 3, 9. 9 is still too small, right? Gotta keep going. 4 and 4, which, just because we're practicing about factor trees, okay? So now, 16 is still pretty small from that, right? So let's look at 5, just in case. All right. So now, 25, bigger than 21. So therefore, 5, we do not have to think about. Okay. Now, let's see here with 21. Is this a prime? Not divisible by 2, right? Okay. Well, let's look at 3. All right, so 3. 3 times 5, because we like to do 5s first because those are pretty easy, right, is 15. Then we have 3 more is 18. 3 more on top of 18 is 21. That's our magical number, right? So let's take our calculator out. And 3 times what equals to 21? The answer is 7. 3 times 7 equals to 21. Since we found one case, 21 is composite. Okay. And that is how we deduce whether or not numbers are primes. Now, let's take it a step further. 7, right? Are there 2 integers that can multiply together to equal to 7? There is not. 7 is also a prime. 3 is a prime, 7 is a prime, 2 is a prime. And then, of course, 17 is a prime that we looked at. So what I want you to do for homework in the discussion post is I want you to find for me some more primes. Okay? See if you can find some more. All right? Because there is an infinite number of primes. Believe it or not. See if you can find another one besides the 2, 7, 5, and the 17. Besides those, see if you can find some more. Okay? So now, what we are going to talk about is we are going to go into how we can go through these factor trees a little bit easier. Okay? Because this is multiplication that is going on with these branches, right? But the operation of this big number getting to these smaller numbers is division. Division reduces the original amount. Think about it. If I had 4 groups and I had 2 muffins, right? So, or how about this? If I have 4 muffins and I have 2 people, right? How can I evenly give the amount of muffins to those 2 people? Well, that's simple. That's 4 divided by 2, which equals to 2. Smaller number, right? Becoming smaller. Multiplication, the number obviously becomes a lot bigger and quickly too. Division makes the number smaller. Okay? Now, let me now go over what we call divisibility rules. Okay? I'm going to go ahead and erase all this stuff right here. And also, if you'd like to, you don't have to watch the entirety of the video. If you understand what I'm going to be going through, very well. Or if it seems like I'm taking too much time on these concepts, you can always go ahead. Okay? I am okay. I am not offended. I understand that we are all students that are trying to get through this thing, and this whole process is just a little bit difficult. Okay, so now, divisibility rules. Divisibility. Lots of I's in this thing. Rules. Visibility rules. Now, these rules are attached to, once again, integers. That's all we're dealing with, is just looking at the divisibility rules of integers. Because a fraction is made, or a rational expression is made from integers. Okay? So, divisibility rules. How we know when something is divisible by a number. Okay? Well, in order to do that, we need to look at our multiplication of these numbers. So first, let's start with our smallest number, number 1. Now, unfortunately, 1 is not very fun, right? Because you could take 3 divided by 1 is 3. 4 divided by 1 is 4. 1 million divided by 1 is 1 million. Not really any kind of rule there, right? Except that when you take just 1 divided by that number, you get that same number. Okay? So I'm not going to write it down because that's kind of more of a given, but it's something we should know for later on. Okay? All right, how about 2? When is a number divisible by 2? Well, let's put some multiples out here, shall we? Okay, so let's see. Okay, 2 plus 2 is 4, right? Then add another 2, so 5, 6, right? So 2, 4, 6. Okay, and then add another 6 on top of that. That's 8, right? Add another 2 on top of that. That's 10. Add another 2 on top of 10. That's 12, right? Now, what do you notice? What type of digit is that last digit? I know this might take you back quite a ways, but for those of you that remember, these are what we call even digits. So if the last digit is even, it's divisible by 2. Okay? So last digit is even. Okay, so that's our rule. So if it's divisible by 2, the last digit is even. Okay. Sounds pretty easy, right? Not too bad. Well, let's work our way through the next one, shall we? But before we do, let's go ahead and take care of the easy ones just to make sure we have them up here, right? 5. When is it divisible by 5? Well, let's think. So 5, 10, 15, 20, 25, 30, 35, 40, blah, 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 right? What are the last digits? 0 or a 5. Okay? So, last digit is 0 or 5. Okay? Now, let's take a look at the next one. The next easy one, right? Well, when is something divisible by 10? 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. The last digit is a 0. Makes sense, right? Last digit is 0. Now notice, all 3 of these rules right here have to do with the last digit, right? We are now going to go into other rules that go past the last digit, okay? Or things that are a little bit more particular, all right? Let's take a look at 3. Okay, so 3, add 3, 3, 1, 2, 3, 6, right? 1, 2, 3, 9, right? 1, 2, 3, and that's going to be 12, okay? Let's see. So, or, if you guys remember Schoolhouse Rock, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. For those of you that remember that, you're welcome. For those of you that don't, your childhood was, unfortunately, taken away from you a little bit too quick. Anyway, that's beside the point. Yeah, don't fire me. Okay. 3, 6, 9, 12, 15, 18, right? Okay. Let's ignore the 3, 6, 9 for a second and just focus on the 12, 15, and 18. All right? So, let's see here. Instead of looking at the last digit, because if you look at the last digit, it goes back and forth, right? Odd, even, odd, even, blah, 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 right? How about this, though? Let's add these two digits together. What's 1 plus 2? 3. What's 1 plus 5? 6. What's 1 plus 8? 9. Do you follow me? When we add the digits, or the sum of the digits, equals to 3, 6, or 9, it's divisible by 3. Let me go ahead and write that down for us, and then I will give you an example. So if it's divisible by 3, the sum of the digits equals to 3, 6, or 9. Let me express it. Okay, let's think about a number. How about 36? Is 36 divisible by 3? Well, let's see. 36 is built of 3 and 6. What is 3 plus 6? 9. Therefore, 36 is divisible by 3. Let's look back at the one that we were doing before, the 21, right? Okay. 2 and 1, right? What's 2 plus 1? 3. 3, 6, or 9. Therefore, it's divisible by 3. Make sense? Okay. That is the rule for if we know it's divisible by 3. Right? Having fun yet? All right. Here comes the fun one. Or at least this is my favorite. It's just really interesting to think about. Do you remember when a number is divisible by 9, or your multiples of 9, that you took your fingers and you put one down, and then you could see how many were left? Okay. How many fingers do I have held up right now? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 fingers, right? Okay. So 9 times that one right there, right? So I have 4, so 4 right here, and 5. So the number of 9 times 5 equals 45. Does that make sense? Now, let's look at it algebraically, and also think about it in terms of what we just learned with the 3. Okay? Let's write down our multiples of 9, though, first, right? So 9, we have 9, 18, 27, 36, right? 45, so on and so forth. Now, add those digits together. What's 1 plus 8? 9. What's 2 plus 7? 9. What's 3 plus 6? 9. What's 4 plus 5? 9. What's 5 plus 4? 9. What's 6 plus 3? 9. They all equal 9. Right? That blew me away when I found that thing out. Or at least like when someone else showed me that. That is how we know it's divisible by 9. Is when we take the sum of the digits and it equals to 9. Okay? So let's go ahead and write down that rule. Okay, so okay. So the sum of the digits equals to 9. And if you end up getting multiple digits, you just keep adding up the digits. Same thing goes for 3. So like, let's say, for example, now we can start looking at it this way. How about 37? Okay. 37. Last digit is not even. Last digit is not 0 or 5. And last digit is not 0. Therefore, not divisible by 2, 5, or 10. Right? Let me go ahead and write this number up here so that way we remember it. So, 37. Right? How about 3? Well, 3 plus 7 equals to what? 10. 10 is not the number 3, 6, or 9. Therefore, not divisible by 3. Since it's not the sum of 9, definitely not divisible by 9. But how far did we have to go? Do you remember? Let's look at our squares, or when we multiply the same number twice. Okay, so 37, right? So let's see. 4, 2, 2, 9, 3, 3, 16, 4, 4, 25, 5, 5. 36 is 6 and 6. Okay. 36 is really close to 37, right? Therefore, we only had to look to 6. And what did 6 give us? 36, right? Therefore, this number is prime. So now you have some additional ways of factoring numbers. Now, as I'm in my closing statement, I'm going to say this. Factoring is a big portion of this class, or will be a big portion of this class, and I want you to understand how we factor. Not just numbers, but what we call polynomials. Okay? Factoring is really important because it reduces down higher degreed polynomials. Now, I know that does not make any sense to you right now, but I'm hoping that throughout this course, I can give you hints of what's going to come. So that way, when it actually gets here, it won't be as frightening or it won't be as intimidating as it was initially. Okay? Now, that being said, take a look at your discussion post, and I will be looking forward to seeing your discussion posts and answers by Wednesday of next week. Thank you very much, and I hope you have a wonderful day.